All right, guys, it's time for fun with math. And so today, what are we going to do? We are going to continue on with this lecture. So last time we talked about Taylor polynomials. And so remember the idea. The idea was you could basically use this polynomial to approximate your function. And it turns out the bigger the degree, the better approximation you're going to get. So now we're going to turn our attention to what are called Taylor series. So what the heck is a Taylor series? So a Taylor series now is an infinite sum. So it's going to be a power series. It looks a lot like a Taylor polynomial, but notice it just never ends. It goes plus dot, dot, dot. So it goes on forever and ever and ever. And just a little trivia, if you want to know when a is equal to 0, so when you center your Taylor series at 0, we call it a Maclaurin series. Now also, this series has the property what? So this is the series that has the property, and so let's give it a name. We'll call this T of x. So this series T of x has the property that if you plug in a, it'll be equal to the function at a. If you take the derivative of that Taylor series and then plug in a, it'll be the same thing as the derivative of f evaluated at a. If you do the second derivative and evaluate it at a, it'll be the same thing as the second derivative of the function evaluate a, and so on and so forth. So this just goes on forever and ever and ever. So it's the power series that has this property, right? So if you have a function and you can evaluate it at a and the derivative a and the second derivative, if you want a power series that does that, that is actually the Taylor series, and that's how it's constructed basically. So let's just take a look at some examples here. So we're going to do two examples today. We're going to do find the Taylor series of e to the x and find the Taylor series of 1 divided by 1 minus 2x. So let's go to the first one. And so we're going to use the definition of a Taylor series, and we're going to center it at 0. So we're going to find most of our Taylor series centered at 0, and then I'm going to show you a little trick, a little algebra trick, basically, that you can use often to find the Taylor series centered at any number. But we'll do that much later. And so we're going to find this Taylor series centered at 0, some given function, and then we'll determine the interval of convergence. So we're going to use the ratio test basically to find that radius of convergence, and then we'll test the endpoints to determine where it actually converges exactly. Okay, so how are we going to do this? So here's my function. And so what do I want to do? I want to find this Taylor series, which again is the sum n equals 0 to infinity. And you're going to take the nth derivative of your function, and we're going to center this at 0, so it's going to be of 0, and then divided by n factorial, and then x to the n. So that's the Taylor series of that function f of x centered at 0. Now, we need to find this guy right here. And so how are we going to do that? We're going to do it like we've been doing it. We're just going to make a table. So over here, I'm going to make a table. So here's my n. This will be my nth derivative of x. And then over here, I'll plug in 0 to see what I get. And so for n equals 0, we just have the function e to the x. And so if you want, whenever you put a 0 up here with that little parenthesis, it just means the function. So this is just f of x, which equals e to the x. And then when n is 1, we'll find the first derivative. And of course, that's actually really easy to do because it's just e to the x. Oh, there's a nice little game afoot here. So second derivative is just, again, e to the x, because derivative e to the x, e to the x, and so on and so forth. So it looks like there's a nice, easy pattern. I guess if we do the third derivative, we'll write in parentheses 3 here for the third derivative. And of course, that's equal to e to the x. And so what happens when you plug in 0? So you're going to e to the 0, which is 1, e to the 0, which is 1, 1, 1. So, gosh, you're always just getting out the number 1. So if you have n here, what happens when you plug in 0? I can guess you're going to get 1. And so the Taylor series centered at 0 for this function is going to be equal to what? It's just going to be equal to the sum n equals 0 to infinity of 1 over n factorial x to the n. Or better yet, we could just rewrite this as a sum n equals 0 to infinity of x to the n over n factorial. And so there's the Taylor series representation for that function e to the x. Now, we want to try to determine where it's actually equal to e to the x, and it's equal when it converges. So how do we find out when it converges? We're just going to run this ratio test on it, and that's going to give us this interval of convergence. So remember, the ratio test is just that limit as n goes to infinity, and we're just going to take the nth plus 1 term and divide by that nth term right there. So we're going to take this guy right here, and we'll take x to the n plus 1 divided by n plus 1 factorial, and then we'll divide it by x to the n divided by n factorial. And so then that's going to be equal to this limit as n goes to infinity. And so on top, we have an x to the n. All right, this is x to the n times x divided by n plus, and I should put parentheses around this. And so n plus 1 factorial. And then times n factorial over x to the n. So I separated these guys here. So then you can see the x to the n's are going to cancel. Don't forget that's all an absolute value. And then n plus 1 factorial, remember, that's just n plus 1 times n factorial. So the n factorials are going to cancel too. So that's going to be equal to the limit as n goes to infinity. I have the absolute value of x over n plus 1. And now the absolute value, it only matters on the x because n plus 1 is already positive. So it's just equal to the limit as n goes to infinity of absolute value of x over n plus 1. And now this limit sees this x as a constant, basically, because n is going to infinity. And so this is basically going to equal absolute value of x over infinity plus 1, which is basically equal to 0, right? So this is me sort of thinking here. And so that's always less than 1. So therefore what? Therefore, this power series T of x converges for all x by the ratio test. Oh, for all x, let's do it for all x, implying our r is equal to infinity by that ratio test. And so therefore, what can we say? So therefore, I can say e to the x is equal to that sum n equals 0 to infinity of what? X to the n over n factorial on negative infinity to infinity. And so that's my final little statement there. Right, so this one's really nice. It has a Taylor series representation that's equal to the actual function for all values of x. And sometimes in some textbooks, you can take this as your definition of e to the x. So let me zoom out a little bit so we can see the big picture on this one, because this one's nice. And it's a famous one. E to the x, you'll see it's one of our standard sort of Taylor series representations for a function. Right, so e to the x, cosine of x, sine of x, those are all important ones. Ln of x, all these have nice standard Taylor series representations, which I'll actually show you later in about a week or so. Okay, so there it is, and it's all its glory, basically. So we didn't have to test endpoints because r was infinity. So let's do one more. So let's do one that's a little bit more challenging, and we'll actually have to test the endpoints. So let's look at this one. And so here I have my function g of x, which is equal to 1 divided by 1 minus 2x. And so what am I trying to do? I want to find its Taylor series representation. So that'd be the sum, n equals 0 to infinity. Now I have g, so I'm going to take the nth derivative of g here. So the nth derivative of g evaluated at 0, because again, we're centering at 0, and divide by n factorial, and I have x to the n. And so this basically tells me what to do. It says, go find that nth derivative of g evaluated at 0. So I'm going to make a table over here. So let's make this table. And so here's n. This will be my nth derivative of g of x. And then I'll plug in 0 in the next column. And so what happens when n is equal to 0? So now here, if you write this correctly, it's not too hard to do. So I'm going to write this as 1 minus 2x to the negative 1. And so the first one here is just the function. So 1 minus 2x to the negative 1. And then the next one, we're going to take the first derivative. So what do we want to do? We want to take a derivative of this guy here. So what's going to happen is the negative one's going to fall down. We get 1 minus 2x to the negative 2. It's negative 2 there. And then times derivative of the inside. So derivative of the inside is just a negative 2. And so this is going to be equal to what? This is going to be a 2 times 1 minus 2x quantity, or to the negative 2. And now let's do that again. So let's do this next derivative. So we'll take a derivative of this guy here. So now the negative 2 is going to fall down. We're going to get 2 times a negative 2, 1 minus 2x to the negative 3 now, and then times the derivative inside, which is a negative 2. And so what's that going to equal? Well, we're going to get 2 times 2 times 2 again here. So we're going to get what? 2 cubed times 1 minus 2 to the x to the negative 3. And then we just keep on doing this to see what happens. And I kind of I'm getting a feel for what's going to happen here. So the negative 3 is going to come down. So we have 2 cubed times negative 3 times 1 minus 2x to the negative 4 times the inside, which is a negative 2 again. All right, so what's that equal to? So that's going to be, let me extend this a little further because I need to get a pattern going here. Once I get the pattern going, then I can figure out what's happening. So here, I'm going to have 2 cubed, and I have 3 times 2. So it's really, like I said, 2 to the 4th times a 3, 1 minus 2x to the negative 4th. And let's do this one more time. So let's take the next derivative. So now the negative 4 is going to come down. So I'm going to get 2 to the 4th, a 3 times negative 4, a 1 minus 2x to the negative 5, and then times root of the inside, which is a negative 2. I think I see what's happening. So this is going to be, well, I guess I could put equals on all these guys if I want. So equals here. This guy's equals here. Oops, let's fix that. I didn't mean to put that there. All right, and then finally, this last one's going to be equal to, so I'm going to leave that 3, I have 4 times 3 times 2. So I'm going to leave that alone because it looks like that's a 4 factorial. And then 1 minus 2x to the negative 5. So if I had to guess, so here's my guess. If I had to guess at the next one, and as soon as I can guess at the next one and get it right, then I have a formula in my head, and I just got to unlock it, basically. So I would guess the next one would be a 2 to the, I think probably to the 5th, because that's a 4th, and then that's a 4 factorial, so I bet it's a 5 factorial, and then a 1 minus 2x to the negative 6. And so you can check it. The negative 5 will come down. That'll give me that 5 factorial. And then I'll have 1 minus 2x to the negative 6 times root of the inside, which is 2, which will give me the 2 to the 5th. Yep, that's it. So now what I'm going to do is I'm going to plug in 0 for all these guys. So wherever I see an x here, I'm going to plug in 0. So for the first one, what do I get? I just get a 1. For the second one here, I plug in 0, and I'm going to get a 2. The third one here, I wind up getting a 2 cubed. And then for the fourth one here, I wind up getting a 2 to the 4th, a 2 to the 4th times 3. And then for the fourth one here, I plug in 0 for x, and I get what? I get 2 to the 4th times 4 factorial. And finally, I plug in a 0 here, and I get 2 to the 5th times 5 factorial. And I can kind of work backwards here. So this is the same thing as 2 cubed times 3 factorial. This should be the same thing as 2 squared times 2 factorial. Yep, that works. The same as 2 to the 1 times, goes 5, 4, 3, 2, 1 factorial. Good. And then this should hopefully be 2 to the 0 times 0 factorial. Remember, 0 factorial is defined to be 1, right? So 0 factorial, here, let me get away from my picture. Sometimes my head's up there hiding this stuff. So let me just scoot down a little bit here. All right, so here, this is a 0 factorial is actually equal to 1, right? By definition. Okay, so I think I have it. So let me zoom out a little bit here, and then we can use this table to write down our final formula, because now if you put an n down here, I'm thinking over here it's going to be 2 to the n, because if it's a 5, you put a 5 up there, and then n factorial. And so this will be equal to the sum, n equals 0 to infinity, and I'll replace this with that. And so I have a 2 to the n factorial divided by n factorial, x to the n, which is just equal to, so the n factorials are going to cancel here. So I just get the sum n equals 0 to infinity of what? 2 to the n times x to the n. That's it. All right, so there's the Taylor series representation. Now, we still need to determine where it's going to converge, and where it converges, that's where it's going to be equal to that function. So how do we find out where it converges? Well, we're going to run that ratio test, and that'll tell us the radius of convergence. Then we can use that to determine the interval of convergence. So we're going to look at the limit as n goes to infinity, and we're going to take this guy right here. So take the absolute value, look at the nth plus 1 term. So there's the nth plus 1 term, and divide by the nth term. And so what does that equal to? Well, that's the same thing as the limit as n goes to infinity of the absolute value, and this is 2 to the n times 2, and then times x to the n times x. So I just separate these two guys, and then divide it by, and I have a 2 to the n times x to the n on the bottom. So the x to the n's are going to cancel, the 2 to the n's are going to cancel, and so what do I get back here? This is going to be equal to the limit as n goes to infinity of just this absolute value of 2 times x. Oh, good. So the n just goes away. So this is just equal to 2 times absolute value of x. You can pull the 2 out because it's positive, basically. All right. And so therefore, what do we know? So therefore, t of x converges for 2 times absolute value of x less than 1, which implies absolute value of x is less than 1/2. So just divide both sides by 2, which implies your r is equal to 1/2 by the ratio test. Great. And so now we know where it converges. Well, we know the radius of convergence. Now we need to figure out the interval of convergence. So how do we figure out the interval of convergence? We're going to test those endpoints, right? So for the interval of convergence, we have to come back here. And so remember, we're centered at 0. So here's 0 right here. And so we're going to go up 1/2 and down 1/2. That's what this really means. That's where our x lives. And so we're going to test these endpoints here, negative 1/2 and positive 1/2. And where are we going to test them? We're going to test them back up in our original series here. So I'm going to scoot out just a little bit more, just so you can see what I'm going to plug into. So I'm going to plug in that series up at top. And so how far I can get down here. I think that's good. All right, so I'm going to plug in first. I'll plug in negative 1/2 in for x right here. And this is my t of x. So maybe we'll come down here. And so I have t of negative 1/2 is equal to, and so wherever I see an x, I'm just going to plug in negative 1/2. So that's going to be a sum n equals 0 to infinity of 2 to the n times negative 1/2 to the n. So we'll do that one. Then we'll also do t of 1/2, which equals the sum n equals 0 to infinity. And again, we're just plugging in 1/2 for x now. And so I have 2 to the n times 1/2 to the n. And so what are these two series actually equal to? So this is going to be equal to, and so this will be a sum n equals 0 to infinity. I have 2 to the n, and now this one I can break up. So I can write that as negative 1 to the n divided by 2 to the n. And so you see 2 to the n's are going to cancel. And so this will be a sum n equals 0 to infinity of negative 1 to the n. And we know that thing is going to diverge, and we can just use the divergence test. So this diverges by the divergence test. And then we'll come down here and do this last one. And so what's this going to equal? Well, this is just the sum n equals 0 to infinity of 2 to the n times, and then you can write 1 to the n, but 1 to the n is 1, and then divided by 2 to the n. And so they're going to cancel, and we just get the sum n equals 0 to infinity of 1, which also diverges by the divergence test. Perfect. So now what do we know? So therefore, that original function we had, 1 over 1 minus 2x, is actually equal to this series, the sum, n equals 0 to infinity, 2 to the n times x to the n, right? On what interval? On this interval right here, and these are still parentheses because you don't include those endpoints because they diverge at those two endpoints. So on -1/2 to 1/2. So that's our interval of convergence. And that function y should be equal to that power series on that interval. All right, so not too bad. Let me zoom out so you guys can see the full picture here, right? So this is kind of a long little problem, but it's not that bad once you kind of get it all together, right? So yeah, so it definitely takes a whole page to fit it on. It's actually kind of probably hard to see all the little parts, but you know, big idea is just make a table, right? So I always write down the formula first right here, and I will give you the formula, but you'll probably have it memorized. You'll do enough of these. But I always write down the formula first because it tells me what to do. And then I do what it says. And then once I get my power series representation for my function, then I can apply the ratio test to find out where it converges. So now I know the function's equal to it where it converges, but then I have to test the endpoints, right? To find the interval of convergence, we got to test these endpoints. Once we test the endpoints, we'll find out if it converges or diverges at the endpoints. And then we can say where the function's equal to that power series or when it's equal to that power series on what interval, basically. All right, guys, that's all I got.